Self-inductance, or in other words, inductance of the coil, is defined as the property of the coil due to which it opposes the change of current flowing through it. Inductance is attained by a coil due to self-inductance EMF produced in the coil itself by changing the current flowing through it. If the current in the coil is increasing, the self-induced EMF produced in the coil will opposes the rise of current. That means the direction of the induced EMF is opposite to the applied voltage. If the current in the coil is decreasing, the EMF induced in the coil is in such a direction as to oppose the fall of current. This means that the direction of the self-induced EMF is same as that of applied voltage. Self-inductance does not prevent the change of current, but it delays the change of current flowing through it. This property of coil only opposes the changing current and does not affect the steady current. That is when it flows through it. The unit of inductance is Henry. Expression for self-inductance. You can determine the self-inductance of a coil by following expressions. First is E equals to L di upon dt, or we can say that L equals to E upon di by dt. The above expression is used when the magnitude of self-induced EMF E in the coil and the rate of change of current di upon dt is known. Putting the following values in the above equation as E equal to 1 volt and di upon dt is 1 ampere per second, then the value of inductance will be L, which is 1 Henry. Hence the above derivation statement can be given that a coil is said to have a inductance of 1 Henry if an EMF of 1 voltage is induced in it when the current flowing through it changes at the rate of 1 ampere per second. The expression for the self-inductance can also be given as E equals to L di upon dt, then d upon dt Li. Also E equals to n d omega upon dt, which is then equals to d n omega upon dt. L into I equals to n omega, or L equal to n omega upon I, and which is Henry, where n is the number of turns in the coil, omega is the magnetic flux, I is the current flowing through the coil. From the above discussion, the following points can be drawn about self-inductance. The value of inductance will be high if the magnetic flux is stronger for the given value of current. The value of the inductance also depends upon the material of the core and the number of turns in the coil or solenoid. The higher will be the value of inductance in Henry, the rate of change of current will be lower. 1 Henry is equals to 1 Weber per ampere. The solenoid has large self-inductance.
So as my friend Pranav has explained you about self-inductance, now I'm gonna talk about mutual inductance. So let's start it by knowing its definition. So mutual inductance between the two coils is defined as the property of the coil due to which it opposes the change of current in other coil, or you can say in the neighboring coil. So when the current in the neighboring coil is changing, the flux setups in the coil, and because of this changing flux, EMF is induced in the coil, which is called a mutually inducted EMF, and this phenomena is known as mutual inductance. So let us understand the phenomena of mutual inductance by considering an example. So let's take an example. As you can see in the figure, two coils, which is A and B, is placed nearer to each other. When the switch S is closed and the current flows in the coil is set up the flux phi, which is denoted by phi, in the coil A, and EMF is induced in the coil And if the value of the current is changed by varying the value of resistance R, the flux linking with the coil B also changes because of this changing current. Thus, this phenomenon of the linking flux of a coil A with other coil B is called mutual inductance. So, for determining the mutual inductance between the two coils, the following expression is used, which is Em is equal to M di1 by dt, or we can say M is equal to Em by di by dt. So, let's name it equation 1 for the further use. This expression is used when the magnitude of mutually induced EMF in the coil and the rate of change of current in the neighboring coil is known. If Em is equal to 1 volt and di1 by dt is equal to 1 ampere, then putting this value in the equation 1, we get the value of mutual inductance as M is equal to 1 Henry. Hence, from the above statement, you can define mutual inductance as the two coils are said to have mutual inductance of 1 Henry if an EMF of 1 volt is induced in one coil, or say primary coil, when the current flowing through the other neighboring coil or secondary coil is changing at the rate of 1 ampere per second. Mutual inductance can also be expressed another way as Em is equal to M di1 by dt is equal to d by dt mi1. We can name it equation 2, and Em is equal to n2 d omega 1 2 by dt, which is d omega 2 with respect to d omega 1, which is equal to d by dt n2 into omega 1 2. Let's name it equation 3. Okay, so equating equation 2 and 3, you will get m I1 is equal to n2 omega 1 2, or we can say m is equal to n2 omega 2 with respect to 1, which is n2 omega 1 2 by I1 Henry. The above expression is used when the flux linkage n2 omega 1 2 of one coil due to the current I1 flowing through the other coil are known. So, the value of mutual inductance M depends upon the following factors: number of turns in the secondary or neighboring coil, cross sectional area, and closeness of two coils. In our daily lives, the best example of the mutual inductance is the transformer, which works on the principle of Faraday's laws of electromagnetic induction. Thank you for watching this video. Have a nice day ahead.